Okay. Simple machine. It's more like simple machines. So we looked at levers in great detail, right? And levers are easy ones to look at, but they represent all the rest of the machines pretty easily. So we said a bicep is what kind of lever then? Class 3, right? And remember, how do we remember? FRE 1, 2, 3. So whatever's in the middle, fulcrum, resistance, or effort, right? F goes with 1, R goes with 2, effort goes with 3, right? So effort meaning input, resistance meaning output, right? Okay. So this would be a case where the input force is in the middle, so that's class 3, like catapult. Okay. What about wheelbarrow? We already said, what's that? 2. Yeah, right. The outputs in the middle. Okay. So we did this, right? We looked at class 1 levers. We looked at class 2 levers, right? And we looked at class 3 levers. Okay. Stapler, I mean, that one's a little, I don't know, it's a little ambiguous, but. Okay, so now let's look at inclined plane, right? Inclined plane or a ramp. We've already kind of talked about this a little bit. So we'll use the same definitions as before. So if we go back to this page, clear back here, right here, where we talk about the actual mechanical advantage is always going to be output force, measured output force over measured input force, right? Ideal mechanical advantage, you don't really have to make any force measurements at all. It's all based on the geometry, the physical structure, right? So it's input distance over output distance. So if we look, right, everybody see that? So ideal or theoretical mechanical advantage is always going to be input distance over output distance. So if we look at an inclined plane, define for me what's the input distance. If I'm going to slide this object from here up to there, what's the input distance?
The distance traveled on the incline.
On the incline, right? Because it's where I'm applying the force, right? The input is me pushing on the machine. In this case, I'm just down here pushing on this box, right? So I'm applying the input distance I'm inputting my force through that whole slanted plane, right? What's the output distance?
The height.
The height, because the output distance is, think of it this way, the output distance is what you've accomplished once you're done and you disassemble the machine, right? What did it accomplish? It picked the box up from there, it picked it up to a height of there. Get it? Okay, so that's what the output was, it picked it up vertically. So then if we want to calculate the ideal mechanical advantage, it's simply going to be the length of the inclined plane divided by the height every time. Okay? Make sense?
Yeah.
Okay? So think about the advantages then. The mechanical advantage is obvious, right? I mean, it's potentially you could reduce the force quite a bit. If you make the ramp pretty gradual, you could reduce the force a lot, right? But what's the other practical advantage here? Sometimes the practical advantage is just as important as the actual mechanical advantage that you're buying.
You don't have to use as much.
You don't have to do it in one go, right? It changes the direction in which you're applying the force, right? So it might be more convenient to apply force in that direction than to apply it vertically, because what if you're having to pick it up 10 feet? I mean, you can't do that, right? That's too high. But rolling it up a ramp, you're walking up the ramp with the object, so there's, half the battle here is just that it makes it makes it more practical to accomplish whatever you need to accomplish, okay? Okay, what's gonna be, obviously, what's gonna be the frustrating force here that's gonna frustrate your attempts to move the box up the ramp? Friction, yeah. Friction's gonna be, it's insidious, that's the part that's gonna be, that's gonna cause the machine to be inefficient, right? And ramps a lot of times are pretty inefficient. Okay? What are some things you could do to overcome friction?
Wheels.
Put wheels, yeah. So if you're moving to a new location, moving your house, you rent a U-Haul, so you're pushing this stuff up the ramp, but what are you probably pushing it up the ramp on?
A dog.
Yeah, a dog, right? So you got something that's gonna roll, right? So that helps. Okay. So that one's pretty straightforward. Okay.
Actually, read that because I think you said before.
So the weight's the output force, input force is what you're applying.
Just have to get it mixed up.
Okay, less effort over a longer distance. Okay, rolling an object's good, that works great. You can roll something. All right. All right, so let's look at a quick example of an inclined plane problem. Okay, try that one. Get some scratch paper. Competing for treats here.
So is the advantage the efficiency?
So no. No, what's efficiency?
It's the percentage or fractional number.
Okay, so,
Determined by that.
okay, so one way to calculate it is the ratio of actual mechanical advantage over theoretical mechanical advantage. What's the other way?
The efficiency with conservative and efficiency without conservative force.
Well, okay, but there's another simple way to calculate it. You can calculate it as the ratio of actual to theoretical mechanical advantage. That works. There's another ratio you could use. Get the same answer. Remember?
Force used.
Not force, work. Output work over input work, right? Output work is always going to be less than or equal to the input work. If it's less than, then that means the efficiency is less than 1. Okay? Here, I know what I'll do. I'll make this will be way better. Why didn't I think of this first time? Okay, do this instead.
Oh, okay. Do what instead?
I'll show you. This is big. So this is how we'll do it from now on, because it's easier for me to toss treats out this way. So go to the Simple Machines in-class practice and go to it. Pull one up. Go there. Pull one up. So get a Chromebook.
So that one first of all, or are you gonna put that same one up?
It's the same kind. So if you've done work, you can just change the numbers. That's what you get.
What was that?
Efficiency either equals the ratio of actual mechanical advantage over theoretical mechanical advantage, or output work over input work. So let's do it the first way, first time. What's the actual mechanical advantage here? So we need the ratio of output force to input force, right? So what's my output force? $35.6 times 9.8. It's the weight of the object, right? It's got to be a force. Okay, that's the mass. The weight of the object. So what's that equal to? Somebody? Somebody's got a calculator. Crank that out.
348.88.
Okay, so there's the output force. What's the input force? They give us that, right? Okay. 295.1 newtons. Okay, so actual mechanical advantage is the ratio of output force over input force. So that's 348.88 divided by 295.1, and what's that equal to?
1.18.
Exactly?
Well, 1.18224.
Okay, so roughly, so keep that in your calculator. Somebody keep that in your calculator. So it's about 1.18. Okay? Theoretical mechanical advantage. What's that? What's the definition of theoretical mechanical advantage? What's that going to be? Just in general. Come on now. This is the one that relies just on geometry. Input distance over output distance, right? Okay, so the input distance in this case is the length of the ramp. What's the length of the ramp? 2.55 meters. The height of the ramp? So what's the theoretical mechanical advantage roughly equal to?
2.45.
Okay, so then the efficiency has got to be the ratio of actual mechanical advantage over theoretical mechanical advantage. So you guys keep the real numbers in your calculator. I'm just going to put the approximations up here. And what do we get to our number of sig figs, which is what, 3? So 3 sig figs, what do we get for efficiency?
48.
Okay, so 0.482, which is the same thing as 48.2%, not very much, right? Over half of the work that we did, we lost to friction in that case.
How do you want us to put that in?
Either way, either one of those it would accept.
I got it.
Okay? So what about doing it using the work method, right? That's probably going to be a little bit easier. So output work is just force times distance, right? Output work is output force times output distance. Okay, so we could also do so the output force we said was I already calculated that. It was 348.88 was the weight. Agreed?
You never have to worry about the fact that it's on the incline. Just,
Well, no, you do, but the output work, absent the machine, we picked up a weight
okay,
that weighed that much, right? Input work is what we actually applied
okay.
on the machine. So output work times output distance was 1.04, right? Divided by input force was 295.1 times input distance was 2.55. And we should get exactly the same thing. If you do that, right? You can verify it, but either way. Make sense?
That way it takes a lot less time.
Yeah, I think it does too.
And that's just dependent on how much information is given?
I can't think of a situation where, unless you were like given mechanical advantages directly, where I would probably just do it the work method instead. I mean, if you were, I'll give you some questions where I'll ask you, what's the actual mechanical advantage, part one? Theoretical mechanical advantage, part two. In that case, probably it's easier to just calculate doing the ratio of those two for efficiency. But otherwise, I don't think I would. Okay. All right, back to business here. I'll give you another chance to earn a snack here in a second. So, okay, what about a wedge? Okay, think about a wedge now. If you're splitting wood, right, you're going to use a wedge. Splitting wood, that requires a tremendous amount of force. Can you imagine taking a log and just ripping it apart? I mean, you guys probably can't. I can, but that's a tremendous amount of force, right? Structural integrity of wood, it's massive. So what do? How does that work? A wedge is it's like a double ramp, isn't it? If I cut this in half,
What would you cut a wedge in half with?
Well, I mean, you wouldn't. You wouldn't. It'd just make a smaller wedge. It'd just make a thinner wedge, right? But just for our point, I want to make a point about how this is designed, right? If we split this thing down the middle, what do we get?
Two wedges.
Two
Two planes.
I get two inclined planes, don't I? Right? You see what I'm saying? We get two inclined planes. I get the top one and the bottom one, right? Now, the length, so they're calling the length of the wedge, this is actually, okay, so it's the depth of penetration. I got you. Okay, that makes sense. All right, so as this thing goes into the wood, it's going to spread the wood apart, right? It's going to split the wood apart. So what's the input distance then, right? This is a classic example of a theoretical mechanical advantage or an ideal mechanical advantage that we're calculating. That's always going to be input distance over output distance. So how far did we move the wedge when we drive it into the wood? Yeah, however far it goes into the wood, that's the input distance, isn't it? Right?
Then it
Okay.
moves at T.
What did we accomplish?
The output, which is the hypotenuse distance?
Is going to be the output. I mean, what do we accomplish by driving?
You
move it
separate
T?
it.
The length of the
Separate
base
it by
is
T.
Oh, okay, we separate
Yeah.
the wood. Yeah, we separate the wood by the thickness of the wedge, right? See what we're getting at? So the output distance in this case is just going to be T, okay? So how would you create, like let's say that you were splitting some oak, some really hard wood. What kind of a wedge would you probably want to start with? A thin one, but a very small angle, right?
Long
Because you'd want the mechanical advantage to be really large, right? You'd want the ratio of L over T to be big. So you'd make T smaller, right? That makes sense. You'd want to kind of start a crack in the wood so you could get it starting to split. Now, once you've created a crack and you've weakened the wood a little bit, what could you do then?
Put a bigger one.
You could put a thicker wedge in there, a wider wedge, and that way with fewer, fewer smacks with the sledgehammer, you're gonna get this thing to spread apart enough where it'll fracture, right? But initially, when you've got generate these really large forces to bite into the wood, you wanna use a pretty thin wedge, don't you, right? Okay? How would you, question?
Just a trivial question.
Yeah, no, go ahead.
Is a wedge not an inclined plane just by itself?
I mean, it really is an inclined plane. It's based on the same principle, isn't it? Right, yep.
Does a slingshot fall under any of these basic?
Not really. What's different about a slingshot in any of these? Yeah, you're storing elastic energy in a slingshot, right? So it's, in none of these other ones are you ever really storing any energy. You're doing work on the machine and you immediately get the work out, right? Slingshot, you're storing it in the elastic sling,
So
rubber
this one
band.
works for like static?
Yeah, yeah. If you look at complex machines though, and one thing we haven't quite gotten to this part yet, but what do you think happens when you build, you connect a bunch of simple machines in sequence? Like say you have a lever, you push on a lever and the output end of the lever applies a force to something different, like maybe to a wheel and axle, which we haven't talked about yet.
Car.
I mean, eventually you get a car. It's called, you create what's called you create what's called a compound machine. But if you look at any really complex machine, most of them, I mean, in most cases, you can break it down to just a bunch of little simple machines working in concert together, and that's all it is. Think about a car. I mean, what's a car doing? You've got the camshaft, it's being driven by the pistons, right? Sure, what's the source of energy for the pistons? The input force, input work is being done by exploding the gasoline, right? But once you've harnessed that, that work done by the gas, when you burn the gas, everything else all the way down that whole drivetrain is just a bunch of simple machines connected together, right? Gears, wheel and axle. You're going to turn some corners with the camshaft, when it goes to the axle.
Under, is that just,
Say that again?
is a gear just a lever?
A gear is considered a wheel and axle, which we'll get to. Yeah.
Oh, yeah.
Okay, so there's a wedge. Pretty simple, but it's based on the inclined plane.
Is there any better way to split wood than a wedge? Or no, because it's both basic?
I don't know. I guess you could inject water into a little crack and freeze it or something.
But it's not just.
It takes
Isn't
a
there
while.
already water?
Place in the wet.
That's
It is,
pretty much a
yeah.
wedge, it's the same
Yeah.
thing.
Yeah. The force that's being applied there would just be the expansion of the ice. I mean, no, it's the way we do it for a reason. I mean, I suppose there are other ways, but that's a pretty good way. Okay, what about this? A screw or a jack screw, same thing. What does this do? Now think about which one you suppose this is pretty strongly related to. There's two of them, really.
The wedge.
I mean, it's the wedge. Where's the wedge come from, though? Yeah, the inclined plane. Think what this does now. If I'm turning a screw, the screw is turning through the threads are turning through. It's been bored out, right? So there's a positive and a negative pattern with the threads. So when I turn this thing, those are just sliding past the grooves in the hole that's been drilled out of the material, right? So what's really happening there? Isn't that just the equivalent of sliding something up a ramp? Only the ramp has been wrapped around a core, right?
And the ramp is
You see what I'm getting at?
Whoa.
I mean, really, the ramp has been just wrapped around a core. If you wanted to think about this, I'm not going to be able to draw this very well, but you get an idea. What if you... So let's say here's our ramp. Here's our ramp. Our ramp is in the form of like a plank, right? So we're starting down here, and we've got this long plank that's connecting to something up here, right? So one way to build a stairway would be to just build a long ramp like so. But if you need to conserve space, what are some things you could do? Well, one thing you could do is you could take this long stairway, this long plank, and you could just wind it up around a central core, right? If you did that, you'd get a circular staircase. Oops, that just is gonna go, how might you do that? Kinda like that, right? And there's gonna be the core in the middle, and you just walk up this thing, right, like you're walking up the Astor Column in Astoria. If you're walking up, what's an example of, everyone's been up one of these before, right? You walk up a tower, or you walk up an old building and there's a circular staircase. You're just walking up in circles, right? If you were to unwind that thing, what would it look like? Just one steady, long ramp, right? That's like a screw, okay? So all you did is you just coiled up the ramp around the core. That's really what a screw is, okay? So how could we define the ideal mechanical advantage for a screw? Okay, so there's a couple things going on if we want to do this. You have to look at a couple things here, right? The ideal mechanical advantage is going to be equal to, well, one thing you have to consider is what's the pitch of the thread, right? So between successive, so if I walk around this column to the same spot that's vertically above where I was a little bit before, if you think of this as a stairway, how far have I moved up vertically, right? Isn't that going to be impacted by the angle of the ramp? So what's going to give you a smaller angle, a really high thread count or a really low thread count?
High thread.
High thread count, right? So by thread count, like if you were going to buy screws at the department store, you'd buy, if it's in metric, you'd measure the amount of threads per centimeter maybe, right? I think in America we do it threads per inch, right? So if you have lots of threads per inch, that means you're making lots of windings in order to go up only 1 inch, okay? So this is kind of a cool way to, like if you want to, let's say that you want to draw two pieces of material together if you're building something and you need to get a really tight fit. Like let's say you've got, I do this stuff all the time when I'm building stuff. Like if you're building what am I building? Trebuchet. Okay, building a trebuchet. And there's two parts of the trebuchet that I need to come together, but it's hard to get them to pull together. There's some resistance, right? I got to get them together so I can get maybe the axle hole to go through all the parts where the axle's going to go. Well, how could you do that? How can you apply really large forces to these two pieces of wood, let's say, to get them to pull together like that? You can't. It's too hard. I can't do it with my hands. What could I do? I could. One thing I could do, and this works, this really is a great trick. You could drill a hole, like let's say, I got to kind of draw a picture of this because I really want to share this with you. This is pretty cool. So if I'm trying to pull this piece of wood right here, trying to pull that piece of wood over in this direction a little bit, right? Pull it over to this piece of wood. But they're kind of at an angle and they don't fit very well. But I need to sandwich those together. One thing I could do is I could drill a hole through this one, right? A large hole through that one. And I could drill a smaller hole, pilot hole, into this one. And I could put a screw through this hole so it just starts to bite on that one. And what happens if I turn that screw in then? Yeah, it's going to, when the head of the screw gets to here, what's it going to do? It's going to pull this one with it as this one bites into the wood, right? And you can develop tremendous forces that way. You can pull stuff together using a screw that you had no chance of doing with pliers or with a vice grip or something. I mean, you really get big forces, okay? So if it's really stubborn, okay, say it's metal, say it's not wood, if it's really stubborn and I really got to be able to drive this thing over there, but it's so hard to do that my drill, it maxes out my cordless drill. What kind of a screw would I probably want to trade for the one that I'm currently using?
Higher thread count.
Higher thread count, right? And if you look at the screws that like metal screws, like the kinds of screws that they would use to attach pieces of a bridge together, if you ever look at those, they're hardened steel, and they, just big nuts and bolts go onto those things to pull them together, but they're really high thread counts. So you can generate extremely high forces to get these big compressive forces that hold these pieces together, right? Okay, so what about this other part of it then? So we've got the distance between threads is gonna be one critical part. Does it make sense that that's on the bottom of a fraction? Because the ideal mechanical advantage should increase when the denominator does what?
Decrease.
Gets smaller, right? So that makes sense, doesn't it? If we make the distance between threads smaller, that means a higher thread count, and that means a more shallow ramp. Well, what's the more shallow ramp gonna do? Let's go back and look at our ramps. A more shallow ramp is gonna mean that you're gonna get more length for less height, so you get a much bigger mechanical advantage, right? See what I'm saying? Okay, so that part makes sense. Oops, went too far. So that part makes sense, right? The bottom, as the bottom gets smaller, the fraction gets bigger. Now what about this part right here? What's L?
Radius.
Okay, it's the radius of the screw that you're turning, right? Does it make sense that if I've got a bigger head on the screw, so I can put in a fatter screwdriver, I should be able to turn with more torque? We haven't used the word torque yet, but that's twisting force,
Yes.
right? I should be able to turn this thing more forcefully, right? How could I design something where I need a lot more turning force? What could I do maybe instead of putting a slot on the top of the screw?
So plus.
Okay, yeah. I could do something like that, right? Where I extend it clear out, much further out than the screw, where I actually use a lever to turn this thing, right? Does that make sense? Okay. And so I increase significantly now. I'm increasing the amount of twisting force I can apply, right? So that shows up on the top because mechanical advantage would be proportional to the radius, right, of where I'm applying the force. How far am I applying the force from the center of the screw, right, from the axis of the screw, okay? All right. So that's once again, that works. You can really provide some large forces. I mean, you can, well, jack up a car, right? I mean, if you need to jack up your car to change a tire, what are you doing? Most of the jacks that are going to be in a car are just going to be screw jacks like this, where you're just going to turn. You're going to turn a screw, and it's going to bring these arms. You've seen them before, right? See a screw jack where the screw is going to provide the lifting force that lifts the car. Yep.
What about one of the bigger hydraulic?
So we'll talk about hydraulics in a little bit. It's not technically a simple machine, but I always include it because it's really similar. If you want to, what happens if you live in California and your house is damaged by an earthquake and you have to lift up your house? What do? Screw jack. You can do it by hand. Seriously. You could lift up your house easily by hand if you had a screw jack with a long lever on it. I mean, you could provide a person, if you could push on that thing with, let's do a little calculation. So you guys throw this in your calculator. So if we've got on a screw jack, if the distance between rotations, we got a really fine thread, so that's going to be, let's say, well, somebody Google what's a fine thread count for a screw?
508.
508.
508 per inch?
Threads per inch.
Threads per inch. Wow. Okay, so
Like fine adjustment screws.
Wow. Okay, so 508. Okay, so let's turn that into a distance then. So it's 508
The pitch is,
turns per screw.
wait, what's the pitch? What would the pitch be? That'd be
For
P.
threads.
That's 0.05 millimeters a revolution.
0.05, okay, per revolution. Okay, so there we go. So put this in. So P is equal to, let's record these
That's
numbers.
0.05 millimeters.
0.05 millimeters. So that's 0.00005 meters, right? And let's say we're going to have a lever on that. We're going to have a lever on that we'll just make it even just 1 meter.
These
So if L is 1 meter, let's figure out what the ideal mechanical advantage of that thing is. What's 2 times pi times 1 divided by that number?
125,000.
What is it?
125,000.
So for 1 pound of force, you could apply 125,000 pounds of lifting force. Now, there's going to be friction in there. It's probably, even if it's only 20% efficient, that's a lot. For every pound, I mean, so you could easily pick up a house, right?
The threads would break way.
Not that much. I mean, corner of a house is probably only a few thousand pounds.
Mr. Roy, I feel like the
Yeah.
threads on that would break before that though.
Well,
Those
right.
are really, really thin threads.
Right. And that's probably not the thread count you would use.
No,
No.
that one was actually just from like fine adjusting.
Yeah. So it'd probably be more like a tenth of a millimeter or a half of a millimeter, but still you're going to get huge multiplication of force there.
Do we have anything to distinguish how, like, how much newtons that we can apply for like something really high? Because,
Before you break the material?
well, so we want to know how much, how strong our
Walter.
is robotics, because it has a 483 to 1 gear ratio.
483 to 1?
Yeah.
God, you could
We had a
lift,
lot
I
of extra
mean,
time. We don't know how powerful the motor is though. So
right. But I mean, so, okay, what's going to happen there, first of all, I mean, 483 to 1, yikes. I mean, so even if your motor's pretty weak,
it could be.
you could pick up a ton of stuff, but you got to worry about the structural integrity of.
It's just aluminum.
Yeah, right. So aluminum would be. I mean, you'd want to have titanium, or moly steel, hardened steel,
Wait,
or something.
what are you guys building?
Well, he's building a robot. This got a gear ratio of 483 to 1. So it's gonna creep along. But
It's
if you,
really slow.
yeah. But with a pretty wimpy motor, you could pick up pretty big stuff, though. Yeah.
I'll take a video of it tomorrow. And show
Yeah.
it to you.
Yeah.
Here's that cord again.
Oh, okay.